Okay, so I've drawn this picture to represent two springs, chains, whatever. It could actually be a schematic representing water in two channels coming together. Okay, so the densities are changing and the water now really kind of breaks down there, but still, and it could be like two sound waves, even though they're longitudinal, it could still be a schematic where you've got a wave coming through one tube of say helium and another tube full of argon. Okay. So the point is, what are we going to feel here? Is going to be constructive or destructive interference? Well, since the waves match up, this wave is down and this wave is down. Okay. And since their frequencies match, it seems then that the next peaks, that this peak will come in at the same time as this peak. Okay. And let's just, I'm going to change the picture slightly. Okay. We'll have the thing truncating right here. So it's pretty clear that valley meets valley. And is this thing going to get shook around more or less when this occurs? Okay. Well, it turns out both waves are tending to pull this thing down. And of course, you can superpose the two waves. If you add a valley to a valley, you get a bigger valley. Okay. So you have constructive interference. Okay. Now, will the next peak meet the next peak? Okay. My question is then, will constructive interference continue? The answer is yes. Because frequencies are equal. Well, times and valley of peak are equal. The next peaks arrive simultaneously. And this continues. Now we can write a more rigorous argument for that, but that'll suffice for this relatively brief survey of the essence of wave function. Okay. Okay. We find the ratio mu2 over mu1 according to the picture. Okay, first of all, said, well, would it be the uh, same as the ratio of something, I forget what was said. And I said, well, perhaps, but we don't know that. What do we know? Okay. And then I asked, how do we know that mu2 is different than mu1? Okay. Well, if you got the same frequency, you've got more waves between here and here than you have between here and here in equal lengths. Okay. Specifically, you've got 1, 2, 2.5, 2 3/4 wavelength there, if that's really a value. Okay. And we'll assume it is. So, not drawn perfectly. And here we have what? 1, 2, 3, and half, and another quarter. That's 3 3/4. Okay, so we can say, okay, I'm going to say it this way. You have 3 3/4, okay, which is 15/4. Lambda 1 equals, oh wait, it's 2 3/4. Well, you do lambda 2, 15/4. Lambda 2 is equal to 11/4. Lambda 1 . So the ratio of your wavelengths is 11/15. No, lambda 2 is less than lambda 1. This is 2, it's shorter wavelength, right? So this has to be less than 1. Also, I mean, if you do this, you just multiply both sides by 4, you get 15 of these equals 11 of these, then divide both sides by 15, and divide both sides by lambda 1. Yeah, you know. Okay, you agree? Okay with that? All right. Well, does that help in any way with the densities? How can one wavelength be less than the other when they're at the same frequency? Okay, so your speeds are different. Now, how could your speeds possibly be different? Okay. Well, if the speeds are different, how can the speeds possibly be different? Well, uh, different mass densities are different tensions, right? No, I said the tensions are the same. Tensions are equal. Thus the densities mu1 and mu2 differ. Okay. Well, so I ask, what's the ratio of mu2 to mu1? Any speculation at this point? Okay, so I think we said that this will also be the ratio of the speeds of propagation. And of course, you got the formula, you know, the speed of propagation is frequency times wavelength. The frequencies are the same. So bigger wavelength will imply greater propagation speed, but you can see that. The time from here to here is the same as the time from here to here. Okay, well, this is further than this, right? So if it goes further in the same time, it's moving faster. And the ratio of how far it moved here to how far it moves here is a ratio of the velocity here to the velocity here. And if you want the ratio from here to here, well, you just invert it. And it turns out for that reason, it's the same as the ratio of the wavelengths, because here's a wavelength, here's a wavelength, right? So you want to see that in terms of the picture, and you want to really understand that so that you can be sure that you're using the equations correctly, because if you just use the equations blindly, it's real easy with these very simple equations to write something down backwards. See me do it all the time, okay? But you want to check it against the reality, okay? The equation isn't the reality. The reality is what you see here. The equation just represents aspects of the reality. Don't want to get too philosophical, but that's a very practical insight. Okay, so anyhow, your densities differ, but you still can't get directly to the densities. Okay, we still got one more insight. And you saw this, articulated this. The ratio of your propagation speeds is equal to the ratio of your wavelengths. You can do that with the equation. Since C equals F lambda, it turns out that the only way the C's could be different at the same frequency is for your lambdas to be different, and they're directly proportional. Speed is directly proportional to lambda for a given frequency. So that this ratio is always going to be the same. And that's a statement you really, really want to internalize and understand, because it can be pretty powerful and can save a lot of algebra or justify a lot of algebra, because you generally want to show this algebraically. Okay. Well, how does this help us get to the desired ratio, which is the ratio of the densities? You know, we started by saying, well, we know from our hands-on experience and from other things that the densities do have to differ. So they're going to have some ratio. So what's the final connection here? Okay. C is inversely proportional to the square root of mu. Or mu inversely proportional to c squared. If you solve this for mu, you get mu equals the square root of tangent over c squared, right? So you could say it either way. Okay. Since we know the proportion to c's, follows that mu2 over mu1, 15 over 11 squared, 225 over 121. It's a little less than 1/2. Okay. Approximately 0.5 to the nearest tenth. So we can, from this picture, or from whatever observations we might have made on this wave, conclude that if these things stay in sync, this one has to have about twice the density. Wait a minute, something's wrong. This has to have greater density, so by wonderful proportional reasoning, just fell the heck apart. I don't see what's wrong here, but let's ponder it for a minute and fix it. Apparently, I've kind of lost my mind here. Yeah, this is half of this. But if I divide this into this, I get something close to 2, not 1/2. Okay, so it's just a bonehead brain glitch. Okay. And of course, if we are backing our calculations up in our algebra up with some AI or just simple utilities, we'll eventually get our thinking and our calculations to agree. Okay. And if we came out with 0.5 here, we'd know. I mean, we knew right away that couldn't be. The first thing we saw was that this must be denser than this. Okay. Now we had to go through several steps to reason that out. There are other ways it could have been reasoned out. We could have written equations. Okay. I mean, we could have written I'm just trying to decide how far back we want to go in the equations. Yeah, well, we could have just said, I'm not sure I want to write all these out. I'm not sure. I was not sure it's going to be a problem. Of course, my brain wants to go back to proportionality. But okay. Comparing to write all this out, I'm writing the expressions for lambda 1 and lambda 2, where L is the length. And we can say same length L, and we'll say same frequency F, so F and L stand for the lengths, and the same tension T. So now we can use T, L, and F throughout. So that now C1 equals this, C2 equals this. Just use lambda 1 and lambda 2. And U1 is going to be T over C1, which is going to be then I'll say 11/4 F over L. U2 equals T over C2 equals, straightforward, 15/4 F over L. And now, oh, wait a minute. It's C1 squared and C2 squared. So I was a little careless there. I didn't write my square. And I was going to get the wrong result. I was going to get the same ratio that I had here without squaring it. And I left my tension off. So I could have written all this out from this conclusion. I could have written even a little more out at each step, but it's totally unnecessary. So that's why I advocate proportional thinking when you're making comparisons like this. It's more direct, more intuitive than writing all this stuff out. You get exactly the same result because everything cancels out except that 15/11 squared. Okay. But you should actually be able to do it both ways. Sometimes one is preferable to the other. And for some people, one is preferable to the other. But everybody should understand both. Deeper understanding. I think there's a lot to be learned from situations like this. I've got lengths, frequencies, tensions, and mass densities, all of which affect this situation. Okay, the question of the interference at that end, okay, whether it's constructive or destructive. You could say, okay, we're going to use two strings of the same mass density. I could give you two mass densities, that'll be okay too. But let's say they have the same mass density and everything is the same except the tension. Then what happens? Well, it's like, okay, we can have this wave being driven. Somebody's driving this wave over here at a frequency. Somebody's driving this wave at a frequency. Matter of fact, to drive them both, we could have two strings or two rubber band chains or two metal chains hooked to a meter stick. Okay, one chain hooked to this end, another chain hooked to this end. And we drive it back and forth so that the frequency is the same for both. But we pull back on this one a little bit harder than on this one until we get the waves to meet in such a way that we have one more complete wavelength here than we have here. Okay. Then what's the ratio of the tensions? And did you work it out already? Not surprised. Now, on a kind of a free-form test that I feel free to give on this stuff. Because I've got, the class consists of really bright people who seem to be performing very well. I could ask you to design an experiment to test some situation. Okay. And say that, how would you do an experiment to test what two frequencies we need in order with all the other stuff being constant? Okay. How would you do that? How would we go out in the hall and do that with the change that we've got? Then I could maybe give a hint. We could maybe use pendulums to at least visually tell you how fast to do it, or even use pendulums to drive the thing. It might be complicated. Okay. On a test, I can think in terms of that being a 20-minute problem. One of those where I would recommend that you think it through and then go on to something else and come back to it 2 or 3 times during the time of the test. Revise what you got in. Because while you're working on something else, your brain's still processing. So don't put it past me to ask a question like that. Okay. Again, I recommend you think through this from as many possible points of view as possible. As many possible points of view as you can. Okay. Here I've got a peak of a wave that I assume is traveling along, or maybe it's just sitting there. Okay. In other words, it won't be just sitting there. Maybe it's a harmonic wave where the peaks go up and down along the same point, and maybe it's a traveling wave. It doesn't matter. What I want to know is, what's the acceleration of, let's say, the mass between here and here, where the string is approximately straight. Now, what I'm going to say is, so just the mass and, okay, just the mass, half this distance to the right and half this distance to the left. So the part of the mass corresponds to this vertical line will be right here. I'm actually going to do it over here. I will take the mass here and assume that all the mass in that segment that corresponds to this one sort of is confined to this point. Okay. And maybe even that this segment here can be modeled by the mass between these 2 points, between the 2 halfway points, and a little bit of string to another mass, say a bead here. And then to the right of that, we have another bead representing the mass to the right and left of this line. Okay, so we have this kind of a picture. Does that make sense? And this thing is clearly concave down, so the slope of this little string is going to be different than the slope of this little string. Okay. We also assume that I'm greatly exaggerating the vertical distances. This thing's really vibrating, very small oscillation. It's too big, the model breaks down to an extent. Okay, so I'm going to look at this picture. I'm going to make it bigger. something like this. So I've got a bead here and a bead here and a bead here. Is the net force on this bead back up a second? The reason I said the displacements from equilibrium are small compared to the wavelength was so I could say that the tension remains uniform. Doesn't really, because when this particle displaces from equilibrium, it creates a little more tension. Okay, but the displacement is so small that that extra tension is negligible. Okay, so it's a simplifying assumption, but it works really well as long as your amplitude remains fairly small. Okay, now I'm going to call this y sub I minus 1, y sub I, y sub I plus 1. In other words, I partition these wavelengths, or partition this wave and approximated it by a bunch of beads. And I think maybe you had a question. Had the question, would the acceleration always be toward equilibrium? And the answer is maybe for this wave shape, maybe not. But let's see why the acceleration has to be toward equilibrium for this one, which it would be. Okay. So my question now is, what forces act here? Okay, can you draw that picture? You don't have to label it. Can you just draw the picture and give me arrows for the forces acting in this? Okay, so we have a good picture of the two tensions. And that's where the force is. You're thinking, well, there's a force down here. Why is there a force down here? The only thing that's in contact with this is just a line indicating the displacement. Okay, there's no force here, although the net force will be more or less in this direction. What you have is you have tension here and tension here. That a little longer because these tensions are equal. So I can use the same symbol for the magnitude of the tension, right? Or I can do T1 with an arrow and T2 with an arrow, and note that magnitude of T1 equals the magnitude of T2. So now are these tensions equal and opposite? Yes or no? No. No. Got a quick head shake. Why are they not equal and opposite? Well, because the slope over here is different than the slope here. We're at this portion of the wave, so the slope is changing. Okay. Now, tensions are not equal and opposite. What can we say about T1y plus T2y? Assuming tensions are equal. So T1y plus T2y, well, we can draw a picture. Okay, here's T1. And we can exaggerate a little, so here's T2. Just want to make T2 steeper than T1. They're of equal magnitudes. So I can sketch my y components. Here's T1y. And here's T2y, right? The T1y plus T2y is less than 0, meaning that when we add the two y components, we get a negative resultant, and it's down. Now, T1x and T2x are also a little bit different, but that goes as the cosine of these angles, and these are very small angles. I don't have room to squeeze it in. Should have tried. Small angles imply kind of cheating. Apply if that's EQ, OPP equal and opposite. Okay. Now the argument is simply that the cosine of any angle, any small angle, is very close to 1. The sine of a small angle is approximately equal to the angle. The angle being measured in radians. Yeah, angles have to be. Okay, unless you put units on. Okay, so this tells us that we have a downward F naught equal delta M A. We call this mass our delta M, and this mass which is the bead that concentrates this mass, we'll call delta M. And if we know how many times we divided the string and the mass density, we can figure out as to what delta M is. It's going to be directly related to the increment of distance we're using and the number of divisions. Okay. Now, can we write and let's go ahead and put an I subscript on this and an I subscript on A, because if we do the I net force and the I acceleration, okay? Acceleration of this mass, which is the I mass. So can we write F net? in terms of delta x, y I minus 1, yi, and yi plus 1 are now delta x is the obvious. It's the distance between our, the width of our partitions, okay? That's okay, so can we write this in terms of these quantities? Okay, now I've seen some good stuff being written down. Maybe using some sines and cosines and stuff like that. Turns out that's unnecessary, but it's pretty natural to do that. Okay, I'm going to just redraw this picture. Again, let's exaggerate the change in slope here. Okay, on this picture, I've indicated a right triangle that actually kind of goes from here down to here and over. Its rise is yi minus 1. And since yi minus 1 is bigger, it's going to be negative. Okay, just kind of check that out. And if we're on this side, then this yi minus 1 would be positive. Over here, then we have another triangle, and I'll be a little clumsy to play with it here, but it's going to be similar to this triangle. And this is then yi plus 1 minus yi, and this is still delta x. So now we've got tension. T2 and tension T1 of equal magnitude, only because we assume the distortions are very small. Okay. Then, in terms of these pictures, and these quantities that I've labeled here, what's T1y and what's T2y? Okay, so I got off on the wrong track. I tried to use the Pythagorean theorem, which is natural because you got triangles, but that doesn't work this time. Okay, T1y is just in the same proportion to T as yi minus 1 is delta x. Okay, now T is a hypotenuse, but the hypotenuse doesn't differ much from the x component. Okay, for small angles, T1y is approximately, we'll say, because it's not exactly equal, of what? It's equal to, be careful, okay, yi minus 1 is negative, but T1y is positive. It's going to be the negative of yi minus 1 over delta x times T. That makes sense? This over this is like the sine of this angle, and you multiply the magnitude of this by the sine of the angle, and you get it. It's not really the sine, though, because this over this is really the tangent. But the tangent and the sine are almost the same when the angle is small, because the tangent's the sine divided by the cosine, and the cosine's almost 1. And doesn't vary a whole lot from 1 until you get into some bigger angles than what we're talking about here. So we can make this approximation. And this approximation is going to work as we take the limit as your delta x's approach zero. Okay. So this approximation is just fine since we're going to be taking a limit as everything gets close to zero anyway. Now I'm waving my hands over that a little bit, watch them wave, okay? So what's T2y? Well, T2y is this. Okay. So what's my expression for the net force? Okay, well, T's a factor of both of these, so T is going to be out here. And delta X is going to be out here. So we'll just put T over delta X out here. And now we can just take the Y's. Well, this is yi minus 1 minus yi. And this is yi plus 1 minus yi. So we get, I don't think I left myself enough room to write all the subscript, but yi minus 1 plus yi plus 1 minus 2y sub I. And then that's times T over delta X. What I'm saying is that the slope here is approximately equal to the average derivative on the left, and the slope here is equal to kind of the average derivative on the right. And I'm waving my hands a little because I'm not going to be too rigorous about this. But what's happening is that this expression right here is pretty much the slope to the left. I can do one intermediate step here a little. The dy dx to the left is this. And I think I've got it wrong. Right and left. Because the derivative of y with respect to x to the left is this slope, which is here. Okay, and if you subtract this, you get this. Okay, so we have this done. And this approaches the second derivative of y with respect to x. Okay. I'm still not sure about my signs, so let me think about this for a second. Okay, I wanted to check that against intuition in a different way. You want to check it against the fact this thing's concave down here, so the net force is going to be, the second derivative is going to be negative. So we have this. All right, well, this is just about it. We've almost derived the wave equation. With leaving out a few little details. I don't think I need much more board to finish this. So that F net I is approximately equal to the tension times the derivative of y with respect to x, second derivative of y with respect to x. You divide the delta x here, and we have our second derivative, and you multiply that by the tension. The I acceleration then is equal to F net I over the mass. Not written very well. Okay. Which is tension over mass. Times the second derivative of y with respect to x. So the second derivative of y with respect to t equals tension over mass times the second derivative of y with respect to x. Tension over the delta m. And we have two different kinds of derivatives of y. And this leads us to something that we're going to get to, and we'll have variable calculus within a week. And it's a partial derivative. Now, I'll kind of leave this until next week. And I write this partial derivative soon. that I think you might have seen some of in differential equations. Okay. Delta M equals total mass divided by the number of increments in your partition, etc. You know, we're out of time. You end up with this T over delta M. And that's just T over mu. There's a simple connection there. I didn't leave myself room to really bring it out. That's 1 over the square of your velocity. And we have this equation that's a universal equation for wave motion. Partial differential equation. And the units check out. This is in reciprocal meters. Square. Oh, I said this is 1 over c squared. This is c squared, not 1 over c squared. Obviously. Someone knows quite well. Okay, so now the units match, and I just kind of wrote that down very carelessly. Often it's written with this on the left and the 1 over c squared on the second partial with respect to t. What it comes down to is that the particles here are accelerated toward equilibrium due to the difference in the slopes, or the difference in the derivatives. It's the change in the derivative or the change in the slope that creates the force. That's why we talk about the second derivative with respect to x. And the force is what gives you the acceleration, which is the second derivative of position with respect to time. So it comes down to that in this picture. Is the basis and not far from a rigorous definition or derivation of the wave equation.